Okay, this is our next topic, that is endurance limit approximate estimations. Endurance limit really plays a very important role in design. So here it's estimation, that is the four factor which are affecting on the endurance limit that we are going to see. Let's see this. Now here we know that with the help of laboratory data we can find the precise value of the endurance limit, but it takes a very much more time to prepare an ascent curve based on this data. And that's why the four factors that are required to pay attention for the endurance limit that we are going to discuss, and without any data of the experimental data, or you can say the laboratory data, we can find out the endurance limit. So the four factors are what? The size. Let's see. Fact that these are the factors which are arise on the fact that there are standard specification and the working condition for the rotating beam specification. Rotating beam is a very important part here. Okay, just pay attention on this part. So based on this, a mathematical equation has been generated, that is SE is equal to K KB KC KD into S dash E. Now what is this terms? So Ka is a service factor, which is, sorry, surface finish factor, which is the first factor which we are considering out of four. Second is the size factor, which is also a major factor in endurance limit. Then reliability factor, then modifying factor to account for stress concentration. These are the four factors which we are considering. Okay. Now what is this SE and SE dash? So SE is what? The endurance limit stress for a particular mechanical component subject to reverse bending stress for a particular component. Okay. And this is for rotating beam. S dash E is for rotating beam only. So this thing which we get here. Now some relationship between the endurance limit and the ultimate tensile strength is that for steel it is having 0.5 times SUT, for cast iron 0.4, for aluminum 0.4, for aluminum alloy 0.3. Okay, I'm just giving you this knowledge just to understand for the numerical purpose. Okay, now this is for 50% reliability. This data is based on the 50% reliability. We are going to see the reliability part also. Now let's see the surface finish factor, which is important. We know that fine polishing is not possible, because you know that if you are going to give a fine polishing, definitely you are going to give a very good endurance limit, because it reduces all type of scratches, and scratches is nothing but irregularities, and that produce a stress concentration point also, and affect the endurance limit. So it is impractical for all component, because it will definitely increase the cost. So as I told you that geometric irregularities are present. So endurance limit is reduced to due to introduction of stress concentration at these scratches. So by this we can have this thing. So endurance limit can be reduced due to introduction of stress concentration at this scratches. If we increase the stress concentration at this point. So this is the graph for this. This is the ultimate tensile strength value, and this is the surface finish Ka value. And this is for the manufacturing condition. It's forge, hot roll, machine roll. It is for ground, for polish parts. Like this graph will help you to get the data. While solving numerical, we can check it out. Now the surface finish factor takes into account the reduction in endurance limit due to the variation in the surface finish between the specimen and the actual component. Now it should be noted that the ultimate tensile strength is also a parameter affecting the surface finish. So this is also a point. In surface finish, the equation is based on the experimental data. So by Knoll and Lipson, this is the equation. This is the equation which is used to find out the value of surface vector. That is K is equal to A SUT raised to B. If K is if K is greater than 1, then the set K is equal to 1. Okay, it should not be more than 1. So the value of A and B that we can get from the table. This is the table for it. For machine roll, for hot roll, for forge, for ground. Based on this value, you will get the value of Ka. But the Ka value should not be greater than 1. This is only for the steel component. For different material, a different Ka value we will get. Now, the second factor is the size factor. Size really matters because as the large number of stresses occurs on the surfaces only, scratches occur on the surface. If the area is large, or you can say if the surface is large, definitely more scratches can be done. So if a component is smaller, it will have a good endurance limit. If a component having bigger one, it will have a less endurance. So endurance limit therefore reduces with increasing the size of the component, as I told you. So this is the part here. Now the size factor Kb into account of reduction in endurance limit due to increase in the size of component can be done with the help of this table. See this table and this values. If for 2.79 diameter, d uh, d is here 2.79 is lesser than this d and should be between 51. So 2.79 to 51 kb is this value. For 51 to 254 kb is this value, and for axial loading kb is equal to 1. Here it is also the kb value is given directly, that d is less than or equal to 7.5, then 1. 7.5 greater than 7.5 and lesser than or equal to 50, then 0.85, and d is greater than 50, then 0.75. So as the value of d is increasing, the value of kb is decreasing. This is only for cylindrical component. Now there are different types of components that are available. That's why I told you that it's a very important part, and it's a big one also. So it is difficult to determine the size factor for component having a non-circular cross sections here. So for this we use a effective diameter concept here. Now how this effective diameter concept can be applied for the non-circular cross section, let's see. So Kugel's equality. This is the diagram which we can help to understand the Kugel equality. So according to this Kugel equality, the effective diameter is obtained by equating the volume of the material stress at and above 95% of the maximum stress to the equivalent volume in the rotating beam specimen. So the 95% maximum stress is considered here. Above that, so based on that, this diagram is being prepared. So when these two volumes are equated, the length of the component and specimen cancel out, and only areas need to be considered here. So whenever these two volumes are equated to each other, at that time only area need to be considered and rest things should be cancelled. So the for the rotating beam specimen is subjected to bending stresses. The bending stress is linearly proportional to the distance from the center of the cross section. So here the area is given, that's 895 stress above 95%, that is 0.95 times the d. So based on this, a mathematical formula is developed here. This formula helps you to get the value of size factor. Now the effective diameter of any non-circular cross section is then given by this. For non-circular cross section we will use this formula, and A95 is what? The portion of cross section area of the non-cylindrical part that is stressed between 95% to 100%, and D is the effective diameter of the non-cylindrical part, the part which is not cylindrical. So the formula for area that is stressed between 95% and 50%, this is, yeah, for rotating A95 this is the formula, non-rotating this is the formula, non-rotating this is the formula, non-rotating that is for I section also. For non-rotating solid shaft, A95 should be in this way. So based on these two equations, that is 2 and 3, we will get the D as 0.37 times small d. So the above effective diameter is used to find out the size factor for the non-rotating cylindrical component, the component which is not rotating. Now for other sections, for rectangular sections, so width B and H can be considered. This is the B and this is the H. So here 0.95 into 0.05 VH. Based on this you will get a value, and this is the formula for this. So this is actually mean. So similar procedure will be for I section beam, and in this way you will get a formula for each and every section. So the laboratory values of endurance limit. Then now the reliability factor. Next is the reliability factor. Reliability factor is really important because here, based on endurance limit, because on the based on experimentation we have to set one reliability. So that's why a 50% reliability is mostly used, because the standard deviation of endurance limit test is 8% of the mean value. So the reliability factor is 1 for 50% reliability. This means that 50% of the component will survive in the given set of conditions. So whatever the condition is given, we all know that it is really not possible, or somewhat possible also, ki for same condition we'll get the same value, but sometimes it is not happen. That's why this 50% reliability we used to take. So this is the table for it, for 50% reliability. Based on this we get the values. The last factor is the modifying factor to account for stress concentration. So the factor is similar. The stress concentration factor used for cyclic loading is less than the theoretical stress factor. And to apply the effect of stress concentration, the designer can either reduce the endurance limit or increase the stress amplitude. Means if you want, you can increase the endurance limit, that is KD, or we can increase the amplitude, that is KF. So based on this, a formula is generated, that is KD is equal to 1 upon KF. So these formulas help you to find out the value of this factor. So now the endurance limit, we have seen the four factors of an actual component. So SSE of a component subject to fluctuating torsional shear stress is obtained from the endurance limit in reverse bending. SE is the reverse bending, SSE is the component. So the maximum shear stress theory, according to this, SSE is equal to zero point 0.5 times SE, and distortion energy says 0.577 SE. So this equation is a major one which we use for designing a component. Okay, just remember this part for any construction. So bending stress is zero at the center of cross section, negligible in the vicinity of center. It is only the outer region near the surface which is subject to maximum stress. So understand this outer region near the surface which is subject to maximum stress, and nothing else. Therefore, this endurance limit in axial loading is lower than the rotating beam test. This is how we completed this part. So I think you understand this part. Thank you very much.